Hi guys, just thought I'd catch up with some of these podcasts. So, chapter 16, I know we talked about it in class already, but just a quick little refresher. And I'll bring that screen up hopefully. There we go. So, evolution and its evidence. So, initially, of course, fossils were the big thing. And so this one's all about fossils, how we go about dating things, and then this whole idea of geological time and biogeography. So, some big ideas. So, there's our famous friend Charles Darwin. Essentially, the modern theory, based on his work, suggests that life has been on the planet for about 4 billion years and has been changing all that time. Things become extinct, new things arise, all in response to changing environmental conditions. So the environment's a really important factor. So what evidence do we have? Well, from today's conversation, we've got a lot of fossils and the idea of biogeography, so where those fossils arrange themselves in relation to plate tectonics. So fossils, what the hell are fossils? Well, now my head's in the way, if I'm overlying, well, I move myself out of the way. Don't do that. Just got me out of the way. So they're basically preserved remains. So you can have lovely fossils like this one here, a bit of a trilobite, and that shows us where the shell was, but it's actually a cast of that shell. So it's not a true shell, it's a shell that's been replaced by other minerals. We call that a trace, we call that a cast. You have traces, amber of course, preserved parts, but the important thing is that fossilisation is a really difficult process, so that an organism actually needs to die and get buried really quickly and then left undisturbed if you don't get a decent, really good quality fossil. And these don't happen very often. Most fossils are pretty fragmented. The famous fossil dig at Inverloch, which has created some wonderful new finds for Australian science and understanding of our Australian landmass, they find bone shards. The bones are so badly broken up that that's all they have. So you've died quickly, you've been buried quickly, and you've been undisturbed for a long time. Oxygen's been excluded, so you can rot slowly. The hard parts then will leach out, and that gap where the hard parts were gets filled in by minerals in the soil, the surrounding soils, and in time a mould is preserved in the sediment. And of course you want lots of layers of sediment rushing in and just covering over, and you get a nice fossil bed. And so the Inverloch fossil bed is one in a really fast-flowing river. Or it was a really fast-flowing river when it was formed, and so all the bones are broken up and shattered amongst the rocks. So they get fantastic finds, but it's a lot of hard work. Riverlea up in Queensland is a better place, and they've got some really good finds up there. They'll basically buried in the cave. It's lovely caves in South Australia too. So types of fossils and impression, and the classic, is the rock pool like they have in their houses. What's it called? Slate. And the slate rock has these beautiful impressions, it's like the one here of ferns, that sort of thing. All these casts, the sort of stuff you'd find down at Inverloch, although these bones are even too good for Inverloch. Or you have good old Jurassic Park's insect in amber, and these lovely footprints that you find around places, and wonderful footprints along the coast of Western Australia. Unfortunately, very close to a place where someone wanted to do some mining. It's a bit worrying, isn't it? So the age of fossils, of course, is a really important part of why evolution works. And this is a photograph of some stratigraphic layers. So you've got bones trapped here, there's rock and bone in there and there and there, and then some sediments in between that don't seem to carry much at all. They could even be lava flows. So this would be sedimentary. So fossils are found in sedimentary rock, stuff that's been deposited from erosion material, whereas this is free of any fossils and could well be a lava flow. So we could have lava, some sedimentation over a period of time, another lava flow as the volcano's gone off again, then a thin period of sedimentation and another lava flow, some more sedimentation, a long, big lava flow, more sedimentation, more lava. The important thing is this one down here is oldest, this one here is youngest, and if it contains what we call index fossils, fossils of known age from around that occur around the world at the same time, then we look at that and say, okay, That fossil is known to be about 70 million years old. This layer here formed 70 million years ago. And you work your way up. So it's relative. It's using stratigraphy of rock deposits and fossil deposits, and then relative age of the rock in comparison to the deposits. So it's not an absolute age, it's a relative age. To get an absolute age, then we can use radioactive isotopes. The two main ones, and there are a number, the two main ones use the carbon-14, and we can use those reasonably accurately up to 40 to 50,000 years. But once you get beyond that, we tend to use potassium argon. But it's the same technique. You find your fossil, you take a small sample of your fossil, really small, if we're talking about small crystals, you then put them in a laser beam and destroy them and measure what comes off. And so what's being emitted is then counted, and we know the right ratio of carbon-14 to nitrogen decay to give an age. So we look at that ratio, or potassium to argon to work out that age. So it's a ratio of the two isotopes. That gives us an idea how old things are, and that's absolute. Of course, you don't want to do that if you're going to go small fossil. So if you've got lots of fossils, you can sacrifice some. If you don't have lots of fossils, and apparently the number of fossils of humans found so far would well and truly almost fill my office. There's not much out there. So you don't really want to be using too many pieces of your fossils in radioactive isotope testing, because it does destroy the fossil. There's also things like electron spin resonance and luminescence techniques, which don't tend to get a question about them in the exam. Just worth knowing you can do other things. There are other chemical build-ups we can take from fossils and work out age. Teeth are very good, tooth enamel, that collects chemical information from what your diet's been like. That can be very useful. Of course, this is all based on the Earth being very old. So the theory of evolution in a scientific purpose, from a scientific perspective, relies on the Big Bang happening about 15 billion years ago, and our planet forming about 4.6 million years ago, so about 4.6 billion years of age. Because evolution takes time. It needs lots and lots of time, and those changes occur slowly. So we have this system called plate tectonics, which suggests that the Earth is broken up into a whole lot of different plates, and they're moving all the time. It's a dynamic space. This Nazca plate here is moving towards the South American plate, and the South American plate is moving towards the Nazca plate. So the Mid-Atlantic ridge here is growing. This is a hot spot. We know it's a hot spot as the Galapagos Islands, and that's moving also towards the South American plate. So it's more new islands coming up and old islands disappearing. Darwin, if he went and visited Galapagos now, would find it was different to when he saw it a couple hundred years ago. It's been quite a dynamic area. And then, of course, along that plate margin, you've got the what's the name of those? The Andes Mountains. The Andes Mountains down the coast of South America. You flow that through, and you come along the Rocky Mountains all the way through the Sierra Madre, Rocky Mountains of the United States, and Rocky Mountains of Canada, all the way along that fault line. And of course, San Andreas Fault's quite a famous fault. Across here you find chains of volcanoes forming islands, and Japan's a chain of islands, Indonesia's a chain of islands, Papua New Guinea, all very active. We haven't got time for a geology lesson now. I'm getting carried away. So always of interest. So essentially these things are always on the move, because underneath them is a lot of heat, a whole lot of molten rock. Molten rock's fairly viscous, so it's not moving rapidly, but it still rises and falls in a convection current and cools, dragging the plate above it with it. So once upon a time we had a thing called Pangaea, and there was just one big landmass. It broke up into Laurasia and Gondwana, and of course they're now broken up into the position of the continents as we know them now. But they're all moving. We're moving north. So everything's moving and moving slowly. You don't need to know geological time, but essentially it's all divided up. So we've got 4.6 billion years back here, up to our recent time, the Holocene, and there's huge change through that period. There's been 5 major extinction events in that time. The one we all know about is the big one here, about 65 million years ago, when the dinosaurs disappeared. But before that, there were also a number of major extinctions that took out most of the living things on the planet. And in the Holocene, we are now living through the 6th major extinction event, and it's been caused by us. Environmental change causes extinction. It also causes speciation. It gives other species opportunity to move into empty niches. It just takes longer for that to happen. So we see extinction in our lifetimes. We don't see speciation in a human lifetime, but we will see new species arising, and we still find that we don't really know all the species yet. So we have the Precambrian, when life first starts. These stromatolites still existed over in Western Australia. I'll quickly go through these, and it's not a big deal. The Paleozoic, the Mesozoic. We've got a lot of our landforms around here were formed during the Mesozoic, where I live in Mount Liza, for instance. The Cenozoic, which we now see mammals, birds, insects pouring out. So we talk about biogeography. Now I'm in the way again, aren't I? I'll move myself out the way again. Down there, Gary. And you can watch that thing go around. So one of the things we can do is look at the arrangement of fossils to prove this. So this is all Gondwana. We've got Australia joined to Antarctica, joined through to South America, like we just did with that sack. Africa here. We've got Madagascar joined on there. What's all that breaking up there? Not too sure. A bit of New Zealand across here. What's that? India's attached to ours. But anyway, all that sort of stuff. All attached together, all breaking up. But we can find fossils that are common to all those countries. And even extant animals and plants that are common. So the glaxids, these wonderful fish here that live in Australian waters, are found across Gondwana Islands. The waratah is also a symbol of Southern Africa, as well as, of course, New South Wales floral emblem, and found in New Zealand. These beautiful trees here called Nothofagus are in the fossil beds of Antarctica, and of course all the flightless birds are only found in the southern hemisphere and only live on the southern hemisphere's continents. So no penguins pass the equator, no polar bears come down either. And that's chapter 16. I said, don't do it quickly for a change.